So I think today we're changing a little bit topic, and I'm the first to start this off, and there's some really great talks and conversations after mine, and I will just give an overview of this topic, and we're maybe looking towards observations now. So we've been working at the University of Nottingham, where I'm a research fellow, a lot in this context, and we've published some papers here and have some in preparation, and had the pleasure to working with some really great PhD students. Some have moved on to become postdocs, and they're highlighted here in yellow, and I myself am mentored by some really great people in Nottingham here. So we're interested in galaxy evolution in the context of the cosmic web, and in particular pre-processing. So how galaxies change with the environment before they enter a galaxy cluster. And our work is motivated by observations, and I'm not sure if or how many other people here are interested in target selections and creating OBs, so I will not focus much on that, and hopefully find some things that are interesting for you. So we are using simulations now to prepare for a number of surveys and observations that are starting. I'm particularly involved in the WEAVE survey that just had its first light and is commissioning now, and science verification will start. And so we had a number of questions, how to prepare for that, what can we expect, and characterizing what we might see, so we compare the observations to that. Okay, so the simulations that most of this is based on are the 300. That is a zoom-in simulation, 324 massive clusters were plugged from the multi-dark simulation, and each re-simulation then contains the central cluster with a sphere extending to 15 megaparsec. So this covers the entire infall region, as you can see here in these movies, associated with filaments and with groups, and this accretion into the centered cluster. And this is also the area that we will recover in the observations. WEAVE is this new instrument at the William Herschel telescope. It's a fiber-fed MOS, so multi-object spectrograph with a pretty large field of view, and we're excited to finally get going with that. So we used the time to ask a lot of questions and prepare for that, including can we actually identify filaments in the small area around the clusters? So imagine you really only have a really small area around a booming cluster. Is this possible? So in preparation for the survey, can we use the velocities, or the 3D information to reconstruct the filaments, given that you have massive fingers of God that complicate things? What properties and structures do filaments have in the cluster outskirts? How many galaxies are in each of these environments? So kind of an inventory of how many are in filaments, how many are in groups, how many are backsplashing. What's actually the impact of doing all the simulations, but then the impact of the instrument on this? So not every galaxy will have a fiber on it. Can we still recover that? What happens to galaxy groups as they go into the cluster? Do they go out again like galaxies? How is the star formation gas content affected? Then what's actually the survey? So introducing the survey. Can we measure morphologies? This was related to Euclid. Can we measure photometry? Can we separate mergers from star formation? So there are a number of questions and more questions that we're answering now. I can't tell you all of it, but this is a really broad investigation, all related to cluster outskirts. I'll plug some of these. But given I'm the first to talk about this, so pre-processing, we think, or we can imagine this is really the integration, so integrated effect of a range of processes that happen to galaxies in filaments and groups and outside the cluster, so before it hits the cluster. And so we think that this might have an effect on the transformation of galaxies. So there are 3 areas that we might identify near the cluster: accretion shocks, and I think we might hear more about this, Further out, then there are these groups, or observers call them substructures. It's really difficult to find the groups actually there. And then we don't really know what happens inside them. Same thing as in clusters or not. And then even further, that's what we heard most about now. So the very largest and furthest scales. So near the cluster, the accretion shock, simulation base have found that in close to the shocks, that's the black circles in this from Singer et al., the galaxies will already be stripped of a lot of their gas, about 30% of their gas. And then when they get closer, so when they go towards the virial radius of the cluster, that's when they lose then 70 to 90% of their gas. The loss of gas is important for quenching the galaxy, so for stopping the star formation. But we also know that there are filaments that are funneling into the cluster centers. They might protect the galaxy, and I think we hear more about this in Charlotte's next talk. And also the shocks are surrounding the filament and the cluster as well. So we're currently looking into this with these simulations, and we can see here you have at the center the galaxy cluster and the defined filaments coming out of there. And for example, on the top right, there's the color-coded the Mach number, and in and here's the temperature, which if we look at it a little bit closer, we can see that, for example, at the top there, temperature top, you can see that the center of the filament is colder than its surroundings, so that might be important for supporting or protecting the galaxy. We try to understand a certain thickness or dimension of the filament, so we can actually, in the observations, then determine which galaxies are in those filaments or not, because this kind of view we won't have in the observations, obviously. So we traced, we created the filament characteristic width based on a density profile here. And this is not a very new number, but we can determine that galaxies that are within, thank you very much, within maybe a megaparsec of the center, the spine of the filament, we can call that they are inside the filament. Now, this is a very, again, observation-driven definition. It is not that a filament has a boundary and it stops. It's a very fluffy construct, as you all know. But when we think of observations and we want to attach a label, is it inside or outside a filament, then often the distance to the filament is a crucial number, and then we can say that, okay, if it's within a certain distance, then it is more likely to be affected by the filament. See if we can play this. Here, a very first glance of how the galaxies fall into a cluster in the 300, so how they are funneling to the filaments and into the cluster. We looked at this a bit more in detail to see that the galaxies are just like the gas, are collapsing towards the center of the filament, so the spine of the filament, with a pretty high velocity, about 300 kilometers per second, which also means that the filaments in observations have some sort of fingers of God. Everything is washed out, which makes it challenging to determine the filaments in observations just around clusters. Again, we can see it's a very dynamic area, even though the cluster is, of course, the greatest attractor in the center. Everything is moving towards the filaments and then towards the cluster center and shocking around it. If we go further out, then we are asking about galaxy groups, so the substructures. And the literature often says or equals group processes to pre-processing. So there are reports that up to 50% or so of cluster members have come into the cluster through groups. And then speculations, how important a group is in determining the transformation or the evolution of cluster galaxies. Now, we obviously have to think about that a group is not an isolated thing, but groups fall into the clusters through filaments. So if we follow this logic, we can say that the galaxy is possibly falling into the filament, into a group, into the cluster. So it's important to start thinking about the entire history of a galaxy, rather than, here it is, this is its current environment, therefore it has only been affected by the current environment. It's important to think about that, yes, groups can quench star formation, but not necessarily so. For example, the time that a galaxy is spent as a satellite in a group varies, and it can be relatively short, as has been shown in this paper here. So about 2 to 3 gigayears or less is the average time that the galaxy spends in a group before falling in. And this is a typical time for, or delay time before the quenching starts. So maybe a galaxy that you observe in a group outside a cluster has not yet experienced the quenching in the group. As the group falls into the cluster, it sweeps up more and more galaxies and then deposits it into the cluster, but it takes some time before you can see all of these effects. Undoubtedly, we do see stripping. There is even REM pressure in groups. So similar effects to what you see in clusters may also happen in the groups, but it's not the dominant process. That so, for example, for a typical Milky Way-like galaxy, the inner parts of the galaxy are still very much intact if it's in a group. Now, what happens to the galaxies in infalling groups? So a group that is falling into the cluster, will it survive? Will it come out of the other side? We looked at this, and it turns out that the galaxy groups do not survive the infall of the cluster. So only a very small fraction of groups are actually going through and coming out as a whole group. So if you see a group outside a cluster, it's very likely that it's on its first infall. Here you can see in these diagrams that are radius from the group center. So these are all galaxies in a group. Here are their velocity. This is the center of the group. All these dots are individual galaxies. And as they are falling into the cluster, they become unbound. And many of them stick inside the cluster, and only a few splash out on the other side. But the majority of them become unbound to the group and stick inside the cluster. So even if you observe a galaxy inside a cluster, it may have experienced the group environment before. Now, how do you find out if it's, what was its past history? It's a very challenging question for observers. As is the question of how do you even find groups outside of clusters? There is no one clear way to identify a group. It's baffling to me, but it's a very difficult problem for observers. So inspired by this paper by Joanne Cohn, we asked whether the nodes in disperse are identical to groups near clusters. So these are all groups that are true groups in the simulations. Then we ran disperse and saw if the nodes overlap with the groups as a group finder near clusters. And it turns out that as you go closer and closer to the cluster, there is no match between true simulated groups and the nodes in disperse. Disperse just wants to funnel to the main halo in the center and does not find the groups. This gets better for massive galaxies, but it gets a lot worse if you do it in 2D in observations. So unfortunately, close to a cluster, the dispersed nodes do not overlap with the groups. So finally, what can we expect? How many of the galaxies around the cluster are in which environment? In these groups, in the filaments, and then these yellow objects are galaxies that are backsplash galaxies. So they have gone in and out again and are possibly on their first return. Let me go here. So imagine you are a filament galaxy. The majority will be, so here is the cluster, here is our filament, and the distance to the central halo is plotted here on the x-axis. The majority are pristine filament galaxies. They will have experienced the filament environment. A rigorous definition of a group tells us that maybe 10 to 20% are in groups. So they experience, in addition to the filament environment, question mark, the group environment. But then if you go closer to the cluster, you have up to 60% of these galaxies are backsplash. So they look like they may have been pre-processed by the large-scale structure, but they really have had time in the cluster. And many observations only look at this area, so they're highly contaminated by backsplash galaxies. Now the WEAF cluster survey and also the foremost chances survey, which is very similar but in the south, are probing out to 5 R200. So we're hoping to get the entire range of environments. So here is a breakdown of this. About 50% of galaxies around clusters are in filaments, the others aren't. But the filaments themselves are not homogeneous. They are a combination of just pristine filament galaxies, backsplash galaxies that have gone through the cluster, and group galaxies, depends highly on how you define a group, that have experienced the group environments. All of this is pre-processing and more, I guess, and is one of the key topics of discussion in observations. And then even further out, as I said, this has been the conversation of this conference so far, but I do want to highlight that it is much more challenging, we did not know whether it would be possible to identify filaments in a small area like that, where you have this booming cluster and things sticking out of it. And this is what it looks like for observers. So we might be used to seeing these beautiful things, but in observation, there are a lot more challenges to overcome and questions to ask. And so a lot of my time was spent trying to optimize how we get from this to how do we get the fibers onto the right cluster, onto the right galaxies, to then actually observe the structures here with WEAF. Nearly, okay. Given this time is up, I would like to just tell you that we have 2 sessions during the European Astronomical Society meeting in July. If you're interested or if you're already planning to come, it would be wonderful if you wanted to join us for the Cosmic Filaments in the Universe session. Or also there is an early results from WEAF session. Both of them are special sessions, so they only cover half a day. And in the last 20 seconds, if any of you are in London in the next few weeks, I am curating or have been curating an exhibition there that saw astronomers and artists working together, including on topics of the cosmic web, but also on other topics. There are 7 of these collaborations and experimentations that we're showcasing. So if any of you happen to be in London in the next few weeks, it would be wonderful to see you there. Thank you.
Thank you, that was great. Any questions? Can start here.
Thank you for your good work and good talk. But I'm a bit surprised that only 30% of the galaxies fall into the clusters along the filaments. I just wonder how you actually separate the galaxies falling along the filament and backsplash galaxies, because flyby objects themselves actually move along the filaments. It's splashback flyby object. My second question is about the definition of filaments, because usually clusters are located at the nodes of multiple filaments. So when you actually identify the galaxies along the filaments, which filaments you actually referring to? I mean, there could be multiple filaments, like secondary filaments, or these. So did you consider all of them, or you just consider the thickest filaments?
Okay. Let me repeat your first question. I think was you were surprised by the low number of galaxies that are in filaments, and you asked how. Yeah. Yeah, that's right. That's right.
So how do you separate them? Galaxies along the filaments and backsplash galaxies?
Yeah. So again, this is in the simulations. We detected filaments with disperse in gas. This was done by Charlotte. With halos, this was done by me, and also compared these two things. And then defined a characteristic width, again with all the, is there a boundary, but a characteristic width that we can use for observations to label yes or no inside and outside the filament. And that gave this number. This depends highly on how do you define the filaments? What's the mass limit of defining the filament? What's the mass limit of your observation? So this is a number, I don't have that plot here, that varies depending on your definitions. So it might start with 30, it goes up to 60%, depending on which, if you're only looking at very massive galaxies that are more likely to be in the filaments. Your second point was about the backsplash galaxies. So we can trace the orbit of each individual halo, and so can flag which one has gone through and out again. And so these are what's this yellow cloud around it, are those galaxies that have this tag of having gone through and out again. So one of the questions we asked was, are they then more likely to go back through filaments? And no, they are spreading all over and are equally distributed outside and inside the filaments. So they're both outside and inside the filaments, about 60% if you go really close, but then it drops. It depends actually on the dynamical state of the cluster. But they do not then funnel through the filament back in. And your second question was, sorry. Okay. Thanks.
Other questions?
Thank you. How do you select your galaxies for your observations?
Thanks for asking. So these are all, so the WEAF cluster survey will be 20 nearby clusters. They're all Abell clusters and have been observed with other spectroscopic surveys like WINGS. So they're really well defined in the center. And then for selecting which ones are more likely to be part of the region, I use the J+ narrowband survey, which has good photometric redshifts, to have a first priority of putting the fibers on. Now this shows you that each of these circles here is a pointing for WEAF and has 1,000 fibers. So we cover the clusters with potentially 10,000 fibers, and given our pre-selection, the success rate of them being actually spectroscopic cluster region members is 60% or so. So we expect to get up to between 4,000 and 6,000 objects that are part of the cluster structure in these observations. Out of 5 are 200.
I have a question regarding nodes and groups. Did you mass weight your galaxies, or were there another
Yeah,
way
so the filament extraction was done with mass weighting in the galaxy case. I think that's a simple answer. Yes, they were mass weighted. Why do you ask?
Are they on the edge of the region, like in this picture, or is this just a
Oh,
projection?
this one has one on the edge of the region that we can observe, but there are many more in the center. And this is only one. We have 324. And in fact, Dan Cornwell, the PhD student, has also extended this to another 200 that are at lower masses and also defined the groups. Again, these bubbles here are based on simulations. These are not the nodes. So this is just finding a true group in the cluster outskirts. Once we've done that just using a massive halo and everything that's within 1 R200 of that, call it a group. And another way was to use the bound particles around a halo. So we have 2 ways of defining groups in the simulations. To define groups in observations, so the node technique we think won't work, but there are other ways like friends of friends, density estimations, things like that.
I didn't hear much about what happens to galaxies due to pre-processing. Is pre-processing strong enough to make galaxies red and elliptical?
Yeah, so that's the main conversation here. The assumption is that pre-processing starts the quenching process, and it's most likely not finished because of the time that it spends in, for example, a group. But the idea is that the more dense environments outside of the cluster already onset the quenching, and this can be through stripping of gas or I don't want to use the word strangulation, so what's a nicer word for this? So, yeah, also not so nice. No, not having new gas come into it. But I think we will hear some really nice arguments that this might not be the case. So okay. So I think the point is that this is still very much an open topic, whether and pre-processing has a real impact on quenching, because okay, we know for a long time the galaxies inside a cluster, look different than outside the cluster, that they tend to be more passive, more elliptical, and so the naive or the first order assumption is that a galaxy comes in to the cluster, kind of hits a boundary, and boom, it quenches. And so traditionally there were inside and outside comparisons, and over again people have shown that galaxies inside the cluster look different and have different properties to outside the cluster. Our next step is to understand if this falling in is really the only mechanism to do so, or if this very varied environment and dynamic, constantly changing its current environment has a similar effect, or possibly onsets it, but it might be counteracted through the idea that the filaments could also support the feeding of fresh gas. So my understanding is that it's a very dynamic topic to explore, and to understand why the differences inside and outside are so prominent.
Okay, we're going to have to end. We're going to have to take that over coffee. But thank you very much again, Ulrike.